Next to linear functions, probably the most common function you're going to see in real-world applications, whether it be different sciences or statistics, probability, is going to be an exponential function. So let's go ahead and take a look at what the graph of an exponential function is so we can properly visualize it. So an exponential function is defined as some positive base to the x power. So the variable is actually going to be the exponent. That's where it gets its name, exponential function. And this base, it's important to understand that it is going to be a positive number. So let's go ahead and define some critical values or some footholds to get us started. And these critical values are actually going to be kind of points of change, but also just easy values to plug in. It's easy to plug in x equals 0. And since anything to the 0 power is just 1, that's going to give us the point 0, 1. Now we can go ahead and do the same thing with x equals 1, since 1 is also an easy exponent to plug in there. And so we know we'll also always have a point at 1b, where b is of course the base, so it can change. Now the next kind of critical, it's not a value, but one of the critical characteristics of this function is since we have defined our base to only be greater than 0, well, think about our function here. If we have p of x equals b to the x power, if this is a positive number here, then we in fact know that p of x will always be positive as well. Because if you raise a positive base to any exponent, whether it be positive or negative, it will yield a positive result. Okay, so now what that establishes is that if we look at our graph here, well, we know that all of our y values will be positive for this function. So that means I'm going to create an asymptote right here on the x-axis, and I know that all of my values are going to be above that. So that's a horizontal asymptote. And the equation of that horizontal line is just y equals 0. We now have a few different points to graph as well. So I'm going to go ahead and plot those. I've got one here at 0, 1, and then one at 1b. So now I have these starting points, but I don't really know what my graph is going to look like. So in this case, I'm going to just choose to have a base of 10, since 10 is a nice, easy number to work with. And then let's look at some values and see if we can determine how it will behave. So first, I'm going to start with 0, and I'm going to go in the negative direction. And some of these we already figured out, but if I plug in 0, I'm just going to get 1. Now, if I plug a negative 1 in here, that's going to give me 1/10. If I plug in negative 2, I'm going to get 1 over 100. Negative 3, 1 over 1,000. Negative 4, 1 over 10,000. And so what we find here is the limit as x approaches negative infinity, or as x decreases, of our function here, f of x, well, it's just approaching 0. So I'm going to come over to my graph here, and as x travels to the left, as it gets more negative, well, my y value, or my output, is just going to approach 0. Now, I'll be clear here. It's never going to actually get to 0 or cross the x-axis. It just keeps getting closer and closer. That's a limit. Well, if we looked at it as it turned or went to the left, hopefully you can guess the next thing we're going to do is look at how it behaves when it goes to the right. That's f of x there. Okay, so we've got x and f of x, and let's plug in some values. Again, I'll start at 0, but then in this case, I'll travel in the positive direction. Okay, and then 10 to the 1 is just going to be 10. 10 squared is going to be 100. 10 to the third power is going to be 1,000. 10 to the fourth power is going to be 10,000. And we can kind of see here, well, as x gets bigger, f of x is just going to get bigger and bigger and bigger. So this will actually be approaching positive infinity. And we can write that more formally as the limit as x approaches positive infinity is just going to equal infinity. So if I come back to my graph here, and this kind of makes sense since my two critical values do show that increasing relationship, I can see that I'm gradually getting faster and faster and faster, and then this exponential function is just going to start skyrocketing upwards. It will never actually be vertical though. Just like as I travel to the left, it'll never actually be horizontal. It keeps kind of going down. And again, this is something where if you look at it, it'll effectively be vertical, but it's not actually vertical. One of the things you might point out to me is the fact that I used a specific example here to generalize what these functions are going to do. Now, I was careful in the example that I chose, and since I am comfortable with exponents, I can tell you that even if you did this in general, so you didn't choose a base of 10, you just used a general base like b, the behavior of all exponential functions will mimic this. So you can use this as a guide to look at other exponential functions and predict what they are going to look like. Now in this example, I did use a specific base 10. And you have to be careful when you're doing that because really all I showed is that when the base is 10, this is what it'll look like. However, since I know that nothing I did was really specific to the fact that the base was 10, I can say with relative confidence, and I do know for a fact, that all exponential functions will follow all of these properties. And from there, you can use what we already know about transformations to predict what other functions will look like. Now in this example, I did use a specific base 10. And you have to be careful when you're doing that because really all I showed is that when the base is 10, this is what it'll look like. However, since I know that nothing I did was really specific to the fact that the base was 10, I can say with relative confidence, and I do know for a fact, that all exponential functions will follow all of these properties. And from there, you can use what we already know about transformations to predict what other functions will look like.